If you place the largest known star where our Sun sits, its surface would swallow Jupiter whole and keep going. We're talking about objects so massive, they make our entire solar system look like a marble in a stadium. But here's the problem. We can't agree which one actually holds the title. Right now, there's a star out there called Stephenson 218, sitting nearly 19,000 light-years away in the constellation Scutum. Current measurements put its radius at roughly 2,150 times that of our Sun. That makes it the reigning champion. Except those measurements might be completely wrong. You see, measuring stars this extreme isn't like measuring your height against a wall. These are objects so distant and so large that they constantly pulse and shift, shedding mass like a dog sheds fur in summer. Their atmospheres are so diffuse that scientists can't even agree where one star ends and space begins. And the distances involved. Those numbers come with error margins that could fit entire solar systems inside them. So when you ask if Stephenson 2-18 is truly the largest star in the universe, you're really asking a much more complicated question. You're asking how we measure the unmeasurable, how we know what we think we know, and whether the answer even matters when tomorrow's telescope might rewrite everything. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. Let's start with something familiar to give you a sense of scale. Our Sun is big, really big. About 109 Earths could line up across its diameter. You could fit 1.3 million Earths inside its volume. It's a massive ball of nuclear fusion that's been burning for 4.6 billion years and will keep going for another 5 billion or so. Now forget all that because the Sun is actually tiny. In the cosmic hierarchy of stellar size, our home star barely registers. It's what astronomers call a yellow dwarf, which sounds diminutive because it is. There are stars out there that make the Sun look like a grain of sand on a beach. Red supergiants and hypergiants. These are the true monsters of the cosmos. Take VY Canis Majoris, located about 3,900 light-years away in the constellation Canis Major. This red hypergiant is so large that if you replace the Sun with it, its surface would extend somewhere between the orbits of Jupiter and Saturn. We're talking about a star that's roughly 1,420 times the Sun's radius. You could fit nearly 3 billion suns inside its volume. But VY Canis Majoris isn't even close to claiming the crown anymore. The contest has shifted over the years as our instruments improved and our measurements became more precise. For a while, UY Scuti held the title. This red supergiant in the constellation Scutum was measured at around 1,708 solar radii, back when astronomers thought it sat about 9,500 light-years away. The calculations were straightforward. Measure the star's angular size, estimate its distance, and do the math. Then the Gaia satellite happened. Gaia is a space observatory launched by the European Space Agency, designed to create the most accurate three-dimensional map of our galaxy. It measures stellar parallax, the apparent shift in a star's position as Earth orbits the Sun, with unprecedented precision. When Gaia turned its instruments toward UY Scuti, the results were startling. The star wasn't nearly as far away as everyone thought. Instead of 9,500 light-years, it was closer to 5,900. That might sound like a minor correction, but in astronomy, distance is everything. If a star is closer than you thought, it's smaller than you calculated. UY Scuti's radius estimates crashed from over 1,700 solar radii down to about 755. Just like that, the champion had been dethroned by better data. This is the fundamental challenge with measuring stellar giants. The math seems simple enough. If you know a star's angular diameter and its distance from Earth, you can calculate its actual size. But both of those measurements are maddeningly difficult to nail down with precision. Angular diameter comes from observing how much of the sky a star appears to cover. For most stars, this is an impossibly small measurement. Even the largest stars appear as mere points of light to ground-based telescopes. Astronomers use interferometry, combining light from multiple telescopes to effectively create one enormous virtual telescope, but the technique has limitations. Stellar atmospheres aren't solid surfaces with clear boundaries. They're diffuse clouds of gas that fade gradually into space. Where exactly does the star end? Different wavelengths of light sample different depths in a star's atmosphere. Measure in visible light and you might get one radius. Measure in infrared and you could get something completely different. The star isn't actually changing size between measurements. You're just seeing different layers of its extended atmosphere. Distance measurements face their own problems. Parallax works beautifully for nearby stars, but once you get beyond a few thousand light years, the angles become so small that even Gaia struggles. You're trying to measure something smaller than a human hair viewed from a mile away. The error margins balloon. For Stephenson 218, that distance estimate of 18,900 light-years carries enormous uncertainty. The star sits in a region called Stephenson 2, an open cluster of massive stars. Astronomers can estimate the cluster's distance by observing multiple stars and averaging their measurements, but individual stars within the cluster might sit thousands of light-years closer or farther than the average. Compound that distance uncertainty with the challenge of measuring the star's angular size, and you end up with a radius estimate that's really more of a guess dressed up in scientific notation. That figure of 2,150 solar radii was derived from the star's luminosity and temperature using the Stefan-Boltzmann law, a fundamental equation that relates a star's energy output to its surface area and temperature. But here's the catch. That calculation assumed a temperature of 3,200 Kelvin. Change that temperature by just a few hundred degrees, and the radius changes dramatically. And measuring the temperature of a star that's constantly pulsating, shedding mass, and hidden behind clouds of its own ejected material. Good luck getting that number right. The fact is, Stephenson 2-18 might not be the largest star at all. It might not even be close. There's another contender that deserves attention. WOHG 64, a red supergiant sitting in the Large Magellanic Cloud, a satellite galaxy orbiting the Milky Way. This beast was discovered in the 1970s and has been fascinating astronomers ever since. Current estimates put its radius around 1,540 solar radii, smaller than Stephenson 2-18 on paper, but with one crucial advantage. WOHG 64 might have the most well-defined radius of any stellar giant we've measured. The star is surrounded by a torus, a donut-shaped ring of dust and gas that it's been shedding for thousands of years. This circumstellar environment creates a kind of cosmic ruler. By studying how light interacts with that dust torus, astronomers can constrain the star's size with more confidence than the usual interferometry measurements allow. But even WOHG 64 comes with complications. In 2014, something strange happened. The star appeared to undergo a dramatic transformation, shifting from a red supergiant to what might be a yellow hypergiant. If true, this could signal that WOHG 64 is approaching the end of its life, preparing for a supernova that could happen tomorrow or 100,000 years from now. Yellow hypergiants are rare, so rare that we know of fewer than a dozen in the entire observable universe. They represent a brief transition phase in the evolution of the most massive stars, lasting perhaps only a few thousand years. If WOHG 64 has entered this phase, its size might be changing rapidly. The star we measured yesterday might not be the star we're looking at today. This brings us to a fundamental truth about stellar giants. They're not stable. Our Sun is remarkably consistent. Its radius varies by less than 0.1% over its 11-year activity cycle. You could measure it today, measure it again in a decade, and get essentially the same number. Red supergiants and hypergiants don't work that way. These stars pulsate. Their outer layers expand and contract in cycles that can last months or years. Scuti, for instance, is classified as a semi-regular variable with a pulsation period of about 740 days. Over the course of roughly 2 years, its radius swings from around 1,500 solar radii to 1,900 solar radii and back again. Betelgeuse, the bright red star in Orion's shoulder that everyone knows, does the same thing. It's a pulsating variable that cycles through multiple periods of expansion and contraction. When Betelgeuse famously dimmed in late 2019, astronomers scrambled to figure out whether the star was about to explode. Turned out it had just ejected a massive cloud of dust that temporarily blocked our view. This variability makes the question, how big is this star, almost meaningless without adding, when did you measure it? Stephenson 2-18 might be 2,150 solar radii today, but 6 months from now it could be significantly larger or smaller. We don't have enough observations spanning enough time to map its pulsation cycle, so we're essentially taking a snapshot and assuming it represents the average. The largest stars also shed mass at prodigious rates. VY Canis Majoris loses material 100 times faster than Betelgeuse, which itself loses mass much faster than the Sun. During ejection events, VY Canis Majoris can increase its mass loss rate by a factor of 10 or more, flinging blobs of material into space that each weigh more than twice the mass of Jupiter. Stephenson 2-18 has been estimated to lose about 1.35 times 10 to the -5 solar masses per year. That might sound small, but over time, it adds up. The star is literally evaporating, surrounding itself with shells of ejected gas and dust that make it even harder to measure its true photospheric radius. These massive stars exist right at the edge of what physics allows. There's a fundamental limit called the Eddington limit, which represents the point where a star's outward radiation pressure equals its inward gravitational pull. Get too close to that limit, and the star becomes unstable. Its own light starts blowing away its outer layers. Hypergiants live dangerously close to this boundary. They're so luminous that they're nearly tearing themselves apart from the inside out. This is why they have such short lifespans, only a few million years compared to the Sun's 10 billion. They burn bright and die young, going supernova in spectacular fashion. Actually, that's not quite right. We think they go supernova. Turns out there's a problem. Astronomers have observed plenty of core collapse supernova, the explosions that mark the deaths of massive stars. When they look back at archival images to see what star was there before the explosion, they find red supergiants, but only small ones. Stars below about 18 solar masses and 100,000 solar luminosities. The real monsters, stars like Stephenson 218, VY Canis Majoris and their ilk, don't seem to explode. Or if they do, we're not seeing it. This is called the red supergiant problem, and it's one of the more frustrating puzzles in modern astrophysics. Some theories suggest the most massive red supergiants don't explode in traditional supernovae at all. Instead, they might evolve backward, shrinking and heating up to become hotter, bluer stars before their final collapse. Others propose that these giants do explode, but they're shrouded in so much dust that we simply can't see the fireworks. Recent observations support that second idea. In 2021, astronomers managed to observe a red supergiant during its last 130 days before going supernova. They detected bright radiation and violent ejections of material, behavior that earlier observations had missed. The star was preparing for death in ways that weren't obvious until someone looked at the right time with the right instruments. Another study found that a supernova explosion had originated from a red supergiant wrapped in an unexpected blanket of dust. The dust absorbed and scattered the light from the explosion, making it appear much dimmer than it should have been. If this is common, it would explain why we're not seeing the largest red supergiants explode. They're dying right in front of us, but we're missing it because they've hidden themselves behind veils of their own making. All of this matters for one simple reason. If we can't trust our measurements, we can't crown a champion. Stephenson 2-18 holds the current title with a radius of 2,150 solar radii. But that number is built on assumptions about temperature and distance that might be wrong. UY Scutum was once the largest until better data cut it down to size. VY Canis Majoris has been in and out of the running for years. WOHG 64 might have the best defined measurements, but it's also possibly in the middle of a transformation that's changing its size. And those are just the stars we know about. The Milky Way contains somewhere between 100 and 400 billion stars, and we've only measured a tiny fraction of them. There could be a red hypergiant 10 times larger than Stephenson 2-18, hiding in some dusty corner of the galaxy, completely unknown, because it's too obscured or too distant for our current instruments to detect. Even if we expand our view to the observable universe, with its estimated 2 trillion galaxies, we've barely scratched the surface. The largest star in the universe might be in a galaxy so far away that its light hasn't reached us yet. Or it might have already died, exploding millions of years ago while its final light is still traveling through space. But here's what we do know. We know that stars can grow to truly staggering sizes, dwarfing our Sun by factors of thousands. We know these giants are rare, unstable, and short-lived. We know they shape their environments through powerful stellar winds and spectacular deaths. And we know that every time we improve our instruments, we discover something that challenges what we thought we understood. The question isn't really whether Stephenson 218 is the largest star in the universe. It's whether we're even asking the right question. Size is just one measure of stellar extremity, and perhaps not the most interesting one. What matters more is luminosity, the raw power output. And on that scale, stars like Stephenson 2-18 aren't even in the running. Take R136A1. It's a blue hypergiant in the Large Magellanic Cloud, and it absolutely dwarfs every red supergiant in terms of sheer energy. Its luminosity clocks in at nearly 8.7 million times that of the Sun. That's roughly 20 times brighter than Stephenson 2-18. But its radius? Only about 35 solar radii. You could fit dozens of R136A1s inside Stephenson 2-18's photosphere. So which one is more extreme? The bloated red giant that barely produces heat, or the compact blue furnace pumping out radiation at levels that defy comprehension? Temperature throws another wrench into the comparison. Stephenson 2-18 has a surface temperature around 3,200 Kelvin. That's cooler than a candle flame. R136A1, meanwhile, burns at approximately 53,000 Kelvin, hot enough that most of its energy radiates as ultraviolet light our eyes can't even detect. The difference isn't subtle. It's the difference between a dying ember and a welding torch. Mass complicates things further. Red hypergiants might be enormous in volume, but they're not particularly massive compared to their blue counterparts. Stephenson 2-18 likely started its life with somewhere between 15 and 25 solar masses. R136A1, it weighs in at roughly 215 solar masses, nearly 10 times heavier. That mass dictates everything about how a star lives and dies. Here's the uncomfortable truth. When we focus solely on size, we're measuring the least stable, least representative moment in a massive star's life cycle. Red supergiants and hypergiants are swollen, dying stars in their final throes. They've exhausted their core hydrogen, burned through their helium, and they're desperately fusing heavier elements in shells around an inert core. Their outer layers have expanded to ridiculous proportions, not because they're powerful, but because they're losing control. It's like declaring the largest human being who ever holds the most water weight. Technically accurate, but it misses the point of what makes someone physically imposing. The pulsations make it even messier. Scutum doesn't maintain a constant size. It's a semi-regular variable, which means it expands and contracts over a period of roughly 740 days. During that cycle, its radius can swing between 1,500 and 1,900 solar radii. So when someone asks how big Scutum is, the answer depends entirely on what day you're asking. Catch it at maximum expansion and you get one number. Catch it during contraction and you get another. Neither is more correct than the other. Betelgeuse does the same thing. Multiple pulsation cycles overlap, some lasting hundreds of days, others spanning years. And they interfere with each other in ways that make the star's behavior chaotic and unpredictable. That's why Betelgeuse's famous dimming event in 2019 caught everyone off guard. The star wasn't dying. It was just experiencing an unusually deep minimum in its pulsation cycle, possibly combined with a massive dust ejection event that blocked some of its light. These stars aren't static objects. They're dynamic, unstable systems that are constantly changing size, and any measurement we take is just a snapshot of one particular moment. Distance remains the biggest problem. The farther away a star is, the harder it becomes to measure accurately. Stephenson 2-18 sits roughly 18,900 light-years from Earth. That number comes from analyzing the star's location relative to the Stephenson 2 cluster and making assumptions about the cluster's distance. But if that distance estimate is off by even 10%, the star's calculated radius changes dramatically. WOHG 64 faces the opposite challenge. It's in the Large Magellanic Cloud, which is actually helpful for distance measurements because we have good data on how far away that satellite galaxy is. But WOHG 64 is wrapped in so much dust that measuring its actual photosphere becomes a nightmare. The dust scatters and absorbs light, creating a glowing envelope that's much larger than the star itself. When astronomers measure the apparent size, they're seeing that envelope, not the star's surface. The recent discovery that WOHG 64 might be transitioning from a red supergiant to a yellow hypergiant adds another layer of uncertainty. If the star is genuinely changing temperature and luminosity, its radius is changing too. The measurements we have might already be outdated by the time they're published. VY Canis Majoris illustrates the problem perfectly. Early measurements suggested a radius exceeding 2,000 solar radii. Then better instruments brought that number down to around 1,420 solar radii. That's a 30% reduction, enough to knock it out of the top spot entirely. The star didn't change. Our ability to measure it did. And that's assuming we're even measuring the right thing. Some stars have such extensive circumstellar envelopes that defining where the star ends becomes philosophical. Is the boundary at the photosphere where most of the light originates, or is it at the outer edge of the extended atmosphere where material is still loosely bound to the star but barely denser than the surrounding space? Different research teams use different definitions, and that produces different results. One paper might report a radius of 1,800 solar radii, while another reports 1,200 for the same star, and both could be technically correct depending on what they're measuring. The variability problem intersects with the measurement problem in frustrating ways. When you're observing a star that's 19,000 light-years away, you can't just watch it continuously. You get snapshots separated by weeks, months, or years. If the star is pulsating with a period of 740 days and you only observe it twice, you might catch it at maximum size both times, or minimum size both times, or somewhere in between. Your measurements will be correct for those specific moments, but won't tell you much about the star's average size. This is why infrared observations have become so important. Red supergiants emit most of their energy in the infrared, and they're often surrounded by dust that glows brightly in those wavelengths. Infrared telescopes can peer through the dust and get clearer views of the star itself. But even infrared observations have limitations, especially when you're trying to resolve the surface of a star that appears as a tiny point of light, even through our most powerful telescopes. Only a handful of stars are close enough and large enough that we can actually image their surfaces directly. Betelgeuse is one. Observations from instruments like the Very Large Telescope Interferometer have produced actual images showing bright spots and dark regions on Betelgeuse's photosphere, giant convection cells where hot material rises and cool material sinks. Those images are blurry and low resolution by Earth standards, but they're revolutionary for stellar astronomy. For more distant giants like Stephenson 218, we don't have that luxury. We can't see the surface, We can only infer its properties from the total amount of light reaching us, the star's color, and mathematical models of how stellar atmospheres behave. Those models are sophisticated and well tested, but they're still models. They make assumptions about things like the star's chemical composition, its rotation rate, and the structure of its atmosphere. Change those assumptions, even slightly, and you get different results. The chemical composition issue is particularly tricky. Red supergiants have processed a lot of their original hydrogen into heavier elements, and they've mixed some of that processed material up to their surfaces through convection. Different amounts of elements like carbon, nitrogen, and oxygen affect the star's opacity, how easily light can escape from the interior. Higher opacity means the star has to expand more to release the same amount of energy. So two stars with identical masses and luminosities could have different radii just because they have different chemical makeups. Then there's the question of what happens in the final moments. The pre-supernova observations from 2021 showed that red supergiants can undergo violent changes in their last few months or years of life. If a star ejects a huge amount of mass right before exploding, its radius could change dramatically in a very short time. We might observe it at one size, and then it could swell or shrink substantially before we get another measurement. None of this means the measurements are useless. They're not. We've learned an enormous amount about stellar physics from studying these extreme objects, but it does mean that declaring a single largest star requires an asterisk the size of Jupiter. Stephenson 218 is the largest star we currently know about, based on our current measurements and our current understanding of its properties. That statement is probably true, but it comes with the implicit understanding that we might be wrong about its distance, its temperature, its variability, or what we're actually measuring when we define its radius. UY Scutum held the title before Stephenson 2-18, and it might reclaim it if future observations revise the numbers again. WOHG 64 might turn out to be larger than both of them once we account for its recent transformation, or we might discover something completely new that makes all of them look small by comparison. The galaxy is vast, and we've barely scratched it. Red hypergiants are rare, maybe a few dozen in the entire Milky Way, but that's still plenty of room for undiscovered giants hiding in dusty star-forming regions we haven't surveyed yet. The infrared satellites like WISE and Spitzer have found thousands of candidates that haven't been studied in detail. Some of them could be larger than anything we currently know about, and that's just our galaxy. WOHG 64 proves that other galaxies have their own populations of extreme stars. The Andromeda Galaxy, the Triangulum Galaxy, the dozens of dwarf galaxies orbiting the Milky Way, each one potentially hosts red hypergiants we haven't identified yet. What's clear is that size alone doesn't capture what makes these stars extraordinary. Their luminosities are staggering. Their mass loss rates are extreme. Their evolutionary timescales are incredibly short, and their deaths are among the most energetic events in the universe. Focusing only on radius means missing the bigger picture. These stars represent something more than astronomical curiosities. They're laboratories for extreme physics. When you compress the entire periodic table into a sphere thousands of times the diameter of the Sun, then watch it hemorrhage mass at rates that would evaporate Earth in centuries, you're witnessing processes that push against the known limits of matter and energy. The Eddington limit defines one such boundary. It's the point where radiation pressure equals gravitational force. For most stars, this balance sits comfortably in the background, but hypergiants dance right on that edge. Picture it this way. The core of a red hypergiant generates so much energy that the photons streaming outward exert physical pressure on the surrounding material. At a certain luminosity, that outward push matches the inward pull of gravity. Cross that threshold, and the star starts tearing itself apart from the inside out. Not catastrophically, at least not immediately, but steadily, relentlessly. The photosphere lifts off in layers like an onion shedding its skin. This is why mass loss rates matter so much. Stephenson 2-18 sheds material at roughly 1.35 times 10 to the -5th solar masses per year. That number looks abstract until you convert it. The star is ejecting about 25 Earths worth of material annually. VY Canis Majoris operates at even higher rates during its most violent episodes, blowing off Jupiter mass chunks in single outbursts. Where does all that material go? It forms nebulae. Complex, asymmetric structures that extend for light years around the parent star. VY Canis Majoris sits inside a reflection nebula containing several tenths of a solar mass. The inner shell spans 140 astronomical units. The outer reaches stretch to 12,000 astronomical units. For perspective, Voyager 1 has travelled about 160 astronomical units from the Sun in over 4 decades. It would take 3,000 years to traverse VY-CMA's nebula at that speed. These nebulae aren't uniform clouds. They're intricate tangles of knots, arcs and filaments, each one a fossil record of past eruptions. Some regions glow bright in infrared. Others appear dark, obscured by dense concentrations of dust. Spectroscopic analysis reveals complex chemistry. Molecules you'd never expect to find in the vacuum of space: water, silicon monoxide, titanium oxide, all forged in the dying breaths of a star that's literally boiling itself away. WO-HG64's dust envelope spans roughly 1 light-year in diameter. It contains between 3 and 9 solar masses of expelled material. Think about that. The star has thrown off more mass than our entire solar system contains in rocky planets, and that ejected material now forms a cocoon so thick that the star itself becomes difficult to observe at optical wavelengths. This is where the yellow hypergiant transformation becomes fascinating. In 2014, observations suggested WOHG64 had changed colour, not over millions of years, over a human lifetime. The spectrum shifted toward shorter wavelengths, indicating a hotter surface temperature. Stars aren't supposed to do that. Red supergiants should cool as they age, not heat up. But the models allow for it under specific circumstances. If a red supergiant sheds enough mass fast enough, it can expose hotter interior layers. The outer envelope thins. The effective temperature rises. The star moves blueward on the HR diagram, becoming a yellow hypergiant before, potentially, evolving into a luminous blue variable, or even a Wolf-Rayet star. This isn't just theoretical speculation. Rho Cassiopeiae, another yellow hypergiant, went through something similar in 2000. It dimmed dramatically, ejected a shell of material, then recovered. The star had blown off part of its outer layers in a titanic outburst. When the dust settled, literally, the spectrum showed it had changed temperature and composition. Yellow hypergiants occupy an unstable region of parameter space. They're too hot to have the deep convective envelopes that characterize red supergiants, but too cool to have the radiatively driven winds of blue supergiants. This makes them prone to violent instabilities. Their atmospheres pulsate. Their mass loss fluctuates wildly. Some undergo periodic eruptions that would make solar flares look like candle flickers. Only about a dozen confirmed yellow hypergiants exist in our galaxy. They represent a brief transitional phase, maybe just a few thousand years out of a star's multi-million-year lifetime. Catching one in the act of transformation is like witnessing lightning strike. It happens fast, and you need to be looking in exactly the right place at exactly the right time. The implications for WOHG 64 are stark. If it has transitioned from red to yellow, it's entering the final chapter before core collapse. Yellow hypergiants don't last. They either explode as supernovae, collapse directly into black holes, or undergo some other catastrophic endpoint we haven't fully characterized yet. This brings us to the red supergiant problem. Theory predicts that most core collapse supernova should come from red supergiants. They're the natural evolutionary endpoint for massive stars. But when astronomers catalogue supernova progenitors, stars identified in pre-explosion images, they find a puzzling gap. Red supergiants explode, sure, but only the smaller ones, below about 18 solar masses and 100,000 solar luminosities. The true behemoths, the VY Canis Majorices, the Stephenson 218S, the massive red hypergiants pushing 40 solar masses, we almost never see them explode, at least not in ways we recognize as standard supernovae. Several explanations have been proposed. Maybe the most massive red supergiants don't explode at all. Maybe they collapse directly into black holes, swallowing their own light before it can escape. Or maybe they do explode, but the explosions are obscured by the dense circumstellar material they've spent millennia ejecting. The 2021 pre-supernova observations support the second scenario. Astronomers watched a red supergiant for 130 days before it detonated. During that time, the star showed violent activity, bright emissions, mass ejections, signs of internal upheaval. Then it exploded. But here's the critical detail. When they went back and looked at archival images, they found the star had been surrounded by dense shells of previously ejected material. When the supernova shockwave hit those shells, it lit them up. The explosion was there. It just looked different because the environment around the star was so cluttered with debris. Another recent discovery reinforced this. A supernova that initially seemed to lack a progenitor turned out to have originated from a red supergiant wrapped in thick dust clouds. The dust absorbed and scattered the light, making the explosion harder to detect at optical wavelengths. But in infrared, where dust glows brightly, the supernova blazed clear. This might solve the red supergiant problem. The massive ones do explode. We're just missing them because we've been looking in the wrong wavelengths and not accounting for how much junk these stars dump into their surroundings before they die. But it raises another question. If red hypergiants are ejecting solar masses of material in their final millennia, what triggers those ejections? What causes a star to suddenly decide it needs to shed a Jupiter's worth of mass in a single outburst? The answer probably involves instabilities deep in the stellar interior. As the core burns through successive layers of fusion, hydrogen, helium, carbon, neon, oxygen, silicon, the energy generation rate fluctuates. Sometimes it surges. The outer layers can't respond fast enough and they puff outward. Other times, energy production drops. The outer layers contract. These oscillations aren't gentle. They're violent, convulsive events that ripple through hundreds of solar radii of stellar material. Add in rotation, magnetic fields, and the complex interplay between radiation pressure and opacity, and you get a star that's fundamentally unstable. Not on the edge of exploding, not yet, but constantly adjusting, pulsating, throwing off mass in irregular bursts that make it nearly impossible to pin down a single size at any given moment. This is why VY Canis Majoris, UY Scuti, and Betelgeuse all show variations in their measured radii, depending on when and how you observe them. They're not lying still for the portrait. They're breathing, swelling, and contracting over timescales of months to years. UY Scuti has a pulsation period of roughly 740 days. During that cycle, its radius changes by hundreds of solar radii. Betelgeuse undergoes multiple overlapping cycles, short-period pulsations, long-period variations, and occasional dramatic dimming events, like the one in 2019 that sparked speculation it might explode. It didn't, obviously. The dimming turned out to be caused by a massive dust cloud the star had ejected, which temporarily blocked our view of part of the photosphere. But the incident highlighted just how dynamic these objects are. They're not static spheres sitting peacefully in space. They're roiling cauldrons of plasma, constantly churning, ejecting, pulsating. Measuring their size requires choosing a specific definition of where the star ends. Is it the photosphere, the visible surface, the point where optical depth reaches a certain value, the radius that contains a specific percentage of the total mass? Different definitions give different answers, sometimes varying by hundreds of solar radii. This ambiguity doesn't make the measurements meaningless. It just means we need to be precise about what we're measuring and acknowledge the inherent fuzziness in trying to draw hard boundaries around objects that don't have them. The extreme luminosities add another layer of complexity. Stephenson 2-18 radiates 436,516 times the Sun's luminosity. That's not a typo. Nearly 500,000 solar luminosities pouring out of a single star. At that output level, the radiation field becomes dense enough to exert significant physical effects on the surrounding material. Photons carry momentum. When you have that many photons streaming outward, they push. This is radiation pressure, and it's what drives stellar winds in hot, massive stars. For red hypergiants, the mechanism is slightly different. The cooler temperatures allow dust grains to form in the outer atmosphere. Those dust grains are excellent at absorbing radiation. The photons hit the dust, transfer momentum, and accelerate the grains outward. The dust drags the surrounding gas along with it, creating a wind. The efficiency of this process depends critically on the dust composition and grain size. Get the conditions right, and you can drive winds with velocities of tens of kilometers per second, carrying away significant fractions of a solar mass per million years. Get them wrong, and the wind stalls. The dust evaporates before it can escape. The mass loss drops. This is another source of variability. Changes in the stellar temperature or density can affect dust formation, which affects mass loss, which affects the circumstellar environment, which affects what we observe. It's a coupled system where everything influences everything else, and small perturbations can cascade into large observable changes. Now imagine trying to model all of this. You need to track nuclear reactions in the core, energy transport through radiative and convective zones, pulsational dynamics in the envelope, dust formation in the outer atmosphere, radiative transfer through optically thick dust shells, and the interaction between stellar winds and the surrounding interstellar medium. Each component requires sophisticated physics, and they all have to work together consistently. Current models can reproduce some aspects of red hypergiant behavior. They predict roughly the right luminosities, mass loss rates, and evolutionary timescales. But they struggle with the details, the irregular variability, the asymmetric nebulae, the occasional dramatic outbursts. These phenomena emerge from processes we don't fully understand yet, which means that when we look at Stephenson 2-18 and declare it the largest known star, we're making that claim based on incomplete information processed through imperfect models. It's probably correct, the measurements are solid enough, but there's always the possibility that we're missing something fundamental about how these objects work, and that's the reality we're dealing with. The largest star in the universe might not stay the largest. It might shrink next year when better data arrives. It might pulsate to twice its current size next month. It might have already exploded, and we won't know for another 18,000 years. Which brings us to something you've probably been wondering. If measuring these objects is so difficult and uncertain, why do we even bother? What's the point of chasing after numbers that might be wrong? Here's what makes it worth the effort. These stars aren't just cosmic curiosities. They're laboratories, natural experiments running at scales we could never hope to replicate. The physics happening inside Stephenson 2-18 right now is pushing against theoretical boundaries we've spent decades establishing. Consider the Eddington limit. It's the point where a star's radiation pressure equals its gravitational pull. Push past that limit, and the star should tear itself apart. The outward force of light becomes stronger than the inward pull of gravity. Game over. Stephenson 2-18 is dancing right on that edge. Its luminosity puts it perilously close to the Eddington limit. How close depends on its mass, which we don't know precisely, but we can make educated guesses based on evolutionary models. Those models suggest it started life with 30 to 40 solar masses. It's shed some of that through stellar winds. Current estimates put it somewhere around 20 solar masses. Run the numbers with those values, and you get a star that's operating at 80 to 90% of its Eddington limit. That's uncomfortably high. It means the radiation field is strong enough to accelerate particles outward at significant fractions of the escape velocity. Small perturbations in temperature or density could tip the balance. The star could enter a phase of enhanced mass loss, losing substantial amounts of material in a relatively short time. This actually happens. We've observed it in other hypergiants. Eta Carinae famously ejected several solar masses of material in the 1840s during what's called the Great Eruption. The star dimmed, then brightened, then dimmed again, all while throwing off mass at rates that would empty the sun in a few thousand years. It created a spectacular bipolar nebula that's still expanding today. VY Canis Majoris shows similar behavior, though on a somewhat smaller scale. High-resolution imaging reveals an asymmetric nebula surrounding the star, composed of discrete knots and filaments of ejected material. Some of these knots contain more mass than Jupiter. They were expelled in discrete events, possibly triggered by pulsational instabilities or convective upwellings that brought extra energy to the surface. Stephenson 2-18 likely experiences similar episodes, We just haven't watched it long enough to catch one in action. The star's mass loss rate is estimated at around 1.35 times 10 to the -5 solar masses per year. That's based on infrared excess and MESA emission from the surrounding material. Those masses are particularly interesting. They form in the dense molecular gas being swept away by the stellar wind, and their properties tell us about the velocity, density, and temperature structure of that wind. The fact that Stephenson 2-18 shows strong master emission suggests it's currently in a phase of active mass loss. The wind is thick enough and structured enough to create the conditions masses need. This might be a temporary state. The mass loss could drop in the future as the star's properties evolve. Or it could increase if the star enters an eruptive phase. None of this is captured in simple radius measurements. When we say Stephenson 2-18 has a radius of 2,150 solar radii, we're summarizing an enormously complex object with a single number. It's like describing a hurricane with its maximum wind speed. Technically accurate, but missing most of the interesting details. The real story is in how that radius changes over time, how it responds to internal dynamics, how it couples to the surrounding environment. Red hypergiants are intrinsically unstable. Their envelopes are barely bound. Pulsations can temporarily lift material well beyond the nominal photosphere, creating an extended pseudo-photosphere that fades back down when the pulsation cycle reverses. We see this behavior in other well-studied red supergiants. Betelgeuse, for instance, goes through regular pulsation cycles that change its radius by several percent. It also experiences longer-term variations that can alter its brightness by more than a magnitude. The famous dimming event in 2019 to 2020 was likely caused by a localized cooling of the photosphere combined with dust formation, but the exact mechanism is still debated. Stephenson 2-18 is probably doing all of this and more. We just don't have the observational coverage to see it clearly. The star is faint, distant, and heavily obscured by dust. Getting high-quality photometry is challenging. Getting spectroscopy is harder. Getting interferometric measurements to directly resolve the stellar disk is currently impossible with existing facilities. So we work with what we have. We combine different types of observations, each with its own uncertainties and systematics. We build models that attempt to capture the essential physics while making simplifying assumptions about the details. We compare predictions to observations and adjust parameters until things roughly match. It's an iterative process that gradually refines our understanding without ever reaching perfect certainty. This is normal in astrophysics. We're trying to understand objects that are fundamentally inaccessible to direct study. We can't send probes. We can't take samples. We can only collect the light they send us and try to decode the information it carries. For nearby stars, we have enough photons to work with that we can extract detailed information. For distant hypergiants, every photon is precious, and we have to squeeze as much science out of them as possible. The payoff comes when we discover something unexpected, when observations don't match predictions, when a star does something it's not supposed to do according to our models. That's when we learn the most, because it tells us our understanding is incomplete. There's new physics to uncover. WOHG 64 recently provided exactly this kind of surprise. Astronomers observing it in 2014 noticed something odd. The star appeared to have changed color, not dramatically, but enough to be statistically significant. Follow-up observations confirmed it. WOHG 64 had transitioned from a red supergiant to a yellow hypergiant. This is not supposed to happen, or rather, it's supposed to happen, but over timescales of thousands of years, not decades. Red supergiants can evolve back toward hotter temperatures as they burn through their nuclear fuel and adjust their internal structure. But seeing it happen in real time was unprecedented. It suggested that either WOHG 64 was going through an unusually rapid evolutionary phase, or our timescales were wrong. The implications are significant. If massive stars can transition between spectral types on human timescales, it means they're more dynamic than we thought. It means the neat evolutionary sequences we've constructed might be oversimplified. Real stars don't necessarily follow smooth tracks through temperature-luminosity space. They can jump around, responding to internal instabilities or mass loss events that temporarily alter their surface properties. This matters for understanding stellar populations. When we look at a star cluster and count how many red supergiants versus blue supergiants it contains, we're using those counts to infer the cluster's age and the initial mass function of its stars. If stars can rapidly transition between categories, those inferences become less reliable. We need to account for the possibility that what we're seeing is a snapshot of a dynamic process rather than a static distribution. Stephenson 2-18 could do the same thing. It could transition to a yellow hypergiant or even a luminous blue variable if conditions are right. The trigger might be enhanced mass loss that removes the outer envelope, exposing hotter layers beneath. Or it might be a change in the core that alters the energy generation rate and forces a readjustment of the entire stellar structure. Predicting exactly when or if this will happen requires understanding the star's current internal state. Which brings us back to the models. They need to track nuclear burning in the core, energy transport through the radiative and convective zones, the structure and stability of the envelope, and the interaction with the circumstellar environment. Each component has uncertainties. Combine them all together and the uncertainties multiply. Current best models suggest Stephenson 2-18 is probably burning helium in its core, with hydrogen burning in a shell. It's past the main sequence, but hasn't yet reached the carbon burning phase. It might spend another few 100,000 years in this state before helium exhaustion forces the next transition. Or it might speed through in 1/10 of that time if mass loss accelerates. The range of possibilities is wide enough that making firm predictions is difficult. What we can say with more confidence is what happens eventually. All roads lead to core collapse. Once the core builds up enough iron peak elements that fusion becomes endothermic rather than exothermic, the pressure support vanishes. Gravity takes over. The core implodes in less than a second, reaching nuclear densities and bouncing back in a shock wave that tears through the overlying layers. Neutrinos carry away most of the energy. What's left drives the supernova explosion that we see as a brief, brilliant flash, except we might not see it. This is the red supergiant problem. Theory predicts that stars like Stephenson 2-18 should explode as Type 2p supernova, the most common variety of core collapse supernova. Observations show that most Type 2p supernovae do come from red supergiants, but only the relatively small ones. Red supergiants above about 18 solar masses and 100,000 solar luminosities are rarely, if ever, observed as supernova progenitors. Stephenson 218 is well above both those thresholds. If it exploded tomorrow, it would be one of the most luminous and massive red supergiant supernovae ever observed. But statistically, we don't see many like it. Either they're not exploding, or they're exploding in ways we don't recognize, or they're obscured by dust. Recent work suggests dust obscuration might be part of the answer. When astronomers went back and examined the sites of known supernovae using infrared observations that can penetrate dust, they found several cases where the progenitor star was surrounded by thick circumstellar material. This material absorbed the optical light from the supernova, making it appear fainter than it actually was. In some cases, the supernova was almost completely hidden in the optical but bright in the infrared. If Stephenson 2-18 is surrounded by substantial amounts of dust, which seems likely given its high mass loss rate and infrared excess, then its eventual supernova might be similarly obscured. We'd see the infrared brightening, but optical telescopes might miss it entirely. This would explain why high luminosity red supergiants appear to be missing from supernova progenitor lists. They're there. We're just not seeing them properly. Alternative explanations involve failed supernovae. Maybe the most massive red supergiants don't explode. Maybe the shockwave stalls before it can eject the envelope. The core collapses all the way to a black hole, swallowing the rest of the star in the process. No bright explosion, just a star that quietly disappears. This has been proposed as a solution to the problem, and there's some theoretical support for it. Simulations show that under certain conditions, the shock can indeed fail, leading to direct black hole formation without a visible supernova. But we don't have definitive observational evidence for failed supernova yet. It's hard to prove something didn't happen. You need long-term monitoring of massive stars to catch them disappearing without exploding. And even then, there are other explanations for why a star might seem to vanish. There's another possibility: evolution backward. Not all red supergiants march straight toward core collapse. Some take detours. The most massive ones might lose so much mass that they shed their hydrogen envelopes entirely, exposing deeper layers. When that happens, the effective temperature rises. The star moves leftward on the Hertzsprung-Russell diagram, transitioning from red to yellow to blue. It becomes a yellow hypergiant, then possibly a luminous blue variable, before eventually meeting its end. This isn't speculation. We've observed stars doing exactly this. WOHG 64 provides a compelling example. Located in the Large Magellanic Cloud, this star was classified as a red supergiant for decades. Recent observations showed something unexpected. Its spectrum changed. The temperature increased. The star appeared to be transitioning toward a yellow hypergiant phase. If confirmed, this would represent direct observational evidence of backward evolution in one of the largest known stars. The implications are significant. If massive red supergiants commonly evolve back to higher temperatures, then the number of stars that actually explode while red decreases. The red supergiant problem becomes less of a problem. The missing high-mass progenitors aren't missing. They've just moved on to different evolutionary stages before exploding. But this raises questions about Stephenson 2-18 specifically. Will it follow the same path? The answer depends on how much mass it loses and how quickly. Current estimates suggest its mass loss rate is among the highest known for any red supergiant, roughly 1.35 times 10 to the -5th solar masses per year. That's phenomenal. At that rate, the star could shed a significant portion of its envelope in just a few 100,000 years. Whether that's fast enough to trigger backward evolution before core collapse is uncertain. The timeline is tight. Carbon burning lasts only thousands of years. Silicon burning is even briefer. Once the core starts fusing silicon into iron, you're measuring the remaining lifetime in days. If the mass loss hasn't removed the hydrogen envelope by then, the star explodes as a red supergiant. If it has, you get a yellow or blue supergiant supernova instead. There's observational evidence for both outcomes. Some supernovae show progenitors consistent with red supergiants. Others show yellow or blue supergiants. The distribution suggests that the evolutionary path depends on initial mass, metallicity, and rotation rate. Higher mass stars with higher metallicity and faster rotation are more likely to lose their envelopes and evolve blueward. Lower mass red supergiants with lower metallicity tend to stay red until the end. Stephenson 2-18 sits in a cluster with moderately high metallicity. Its rotation rate is unknown. Its current mass is estimated at around 16 to 20 solar masses, though uncertainties are large. Given those parameters, backward evolution is possible, but not guaranteed. The star could go either way. Let's zoom out for a moment. Why does any of this matter? Because understanding how the largest stars end their lives helps us understand the chemical evolution of galaxies. When massive stars explode, they inject heavy elements into the interstellar medium: carbon, oxygen, silicon, iron, all the stuff that planets and people are made of. The explosion's energy also triggers new rounds of star formation by compressing nearby gas clouds. The cycle continues. If the most massive stars collapse directly to black holes without exploding, then those elements stay locked inside. They don't enrich the surrounding medium. The chemical evolution of the galaxy slows. Fewer heavy elements mean fewer rocky planets, fewer opportunities for life. On the other hand, if these stars do explode, but we're just not seeing the explosions because of dust, then the enrichment continues as expected. We're simply missing the observational confirmation. Recent infrared surveys are starting to close that gap. By observing supernovae in wavelengths that penetrate dust, astronomers can identify obscured explosions that would otherwise go unnoticed. The early results are promising. Several high luminosity red supergiants have now been identified as supernova progenitors, including some that were heavily dust enshrouded. This suggests that the red supergiant problem might be largely an observational bias. The stars are exploding. We're just not always seeing it in the optical. Infrared astronomy is revealing what was hidden, but there's still the failed supernova scenario to consider. Even if most red supergiants explode, maybe the absolute most massive ones don't. Maybe there's a threshold above which the shockwave always stalls. Theory suggests this might happen for stars with helium cores above about 45 solar masses. The exact number depends on details of the explosion mechanism that we still don't fully understand. If Stephenson 218 has a helium core that massive, it might be a failed supernova candidate. The core collapses. A black hole forms. The envelope falls inward. Within hours or days, the entire star disappears from view. No bright explosion. Just a brief transient as the outer layers accrete onto the newly formed black hole. Detecting a failed supernova is challenging. You need to be monitoring the star beforehand so you know it was there. then it needs to vanish without producing a standard supernova light curve. A few candidates have been identified, but confirmation is difficult. It's hard to prove that a star didn't explode versus being obscured by dust or having an unusually faint explosion. Long-term monitoring programs like the Large Binocular Telescope's Search for Failed Supernovae are addressing this. They observe thousands of massive stars in nearby galaxies, looking for ones that disappear. The results so far are intriguing but not definitive. Some stars have indeed vanished, but whether they underwent failed supernovae or just faded below detection limits remains unclear. Now, here's something that doesn't get discussed often enough. The uncertainty in all these predictions comes down to physics we still don't fully understand. The supernova mechanism itself remains partially mysterious. We know the broad outline. Core collapses, bounce happens, shockwave forms, neutrinos carry away energy. But the details of how the shockwave revives after stalling, how neutrino heating works, how magnetic fields and rotation affect the outcome, these are active areas of research. Current simulations can produce successful explosions for stars up to about 25 solar masses, depending on assumptions. Above that, the results become uncertain. Stephenson 2.18's current mass is estimated at 16 to 20 solar masses, but its initial mass on the main sequence was higher, maybe 25 to 40 solar masses. It's lost a significant amount through stellar winds over its lifetime. What matters for the explosion mechanism is the mass of the core and envelope at the time of collapse, not the initial mass. If the star has lost enough mass that its helium core is below the critical threshold, it should explode successfully. If not, failure becomes more likely. We don't know which scenario applies because we don't know the current mass structure precisely enough. There's another wrinkle: rotation. Fast-rotating, massive stars can produce different outcomes than slowly rotating ones. Rotation affects how mass is distributed, how magnetic fields behave, and how energy is transported during collapse. In extreme cases, rapid rotation can lead to jet-driven explosions that look very different from standard supernovae. These might be connected to long-duration gamma-ray bursts, though that link is still being investigated. We don't have direct measurements of Stephenson 2-18's rotation rate. Its spectral lines are broad, which could indicate rotation, but could also result from turbulence or pulsation. Without resolved imaging or detailed spectroscopic monitoring, pinning down the rotation is difficult. If the star is rotating rapidly, its fate could involve more exotic outcomes. Collapsar models, where the core collapses to a black hole while the envelope forms an accretion disk, become possible. These can produce energetic explosions along the rotation axis, while most of the mass falls back onto the black hole. The result is a supernova that's asymmetric, possibly accompanied by a gamma-ray burst if we're looking down the jet. This is speculative for Stephenson 2-18 specifically, but it illustrates how many variables are in play. The star's ultimate fate depends on current mass, core structure, mass loss history, rotation rate, magnetic field strength, and possibly other factors we haven't even identified yet. What we can say is this: within the next few 100,000 years, give or take, Stephenson 2.18 will undergo core collapse. Whether we see a bright supernova, a dust-obscured explosion, a failed supernova, or something more exotic, depends on factors we're still working to constrain. The odds favor some kind of explosion. Most red supergiants do explode, even if we don't always see it. The question is, what kind of explosion and how bright it will be? If it happens while the star is still red and surrounded by dust, we might need infrared telescopes to catch it. If it evolves blue-ward first, the explosion will be more visible in optical wavelengths. Either way, when Stephenson 218 finally detonates, it will be one of the more luminous supernovae in the Milky Way. The exact peak brightness depends on the explosion energy and how much mass is ejected, but estimates suggest it could reach absolute magnitudes around -18 or brighter. From Earth, at a distance of 18,900 light-years, that would translate to an apparent magnitude of roughly +4 or 5, making it visible to the naked eye. Not as bright as historical supernovae like SN 1006 or SN 1054, which were much closer but still noticeable. A new star appearing in Scutum, shining steadily for weeks before fading. Astronomers worldwide would point every available instrument at it. Neutrino detectors would catch the burst from the core collapse seconds before the light arrived. Gravitational wave observatories might detect signals if the collapse is asymmetric enough. The data would provide unprecedented insights into how the most massive stars die. We'd measure the explosion energy, the mass of ejected material, the composition of the ejector, the structure of the circumstellar medium. All of that would feed back into models of stellar evolution and supernova physics, refining our understanding. But that's in the future. For now, Stephenson 218 continues burning helium in its core, shedding mass into space, pulsating irregularly. It's in a relatively stable phase that could last another 100,000 years or end tomorrow. The uncertainty is part of what makes these stars so fascinating. They exist at the edge of stability, where small changes in internal conditions can have dramatic effects. In a sense, studying Stephenson 218 and its peers is like studying extreme weather on Earth. The basic physics is understood, but predicting exactly when and how a hurricane will intensify or a tornado will form remains challenging. The systems are complex, with many interacting factors. Small perturbations can cascade into large effects. Stellar astrophysics faces similar challenges. We have the fundamental equations, general relativity, hydrodynamics, nuclear physics, radiation transport. But solving those equations for a star with 2,150 times the Sun's radius, blowing off mass at prodigious rates, with a core undergoing nuclear fusion in multiple shells, while the envelope pulsates and convects, that requires approximations, and approximations introduce uncertainties. The next generation of telescopes will help. The extremely large telescope, currently under construction, will have the resolving power to image the surfaces of nearby red supergiants. We'll see convection cells, mass ejections, asymmetries in the photosphere. That observational data will constrain models in ways that aren't currently possible. For Stephenson 218 being so far away, direct imaging remains out of reach even with future instruments. But we can study analogues. Betelgeuse is a red supergiant that's much closer and has been imaged in detail. While smaller and less luminous than Stephenson 218, it provides insights into how these stars behave. The great dimming of 2019 to 2020, when Betelgeuse dropped to half its normal brightness, was likely caused by a massive dust cloud ejected from the star's surface. Studying that event in detail gave us clues about mass loss mechanisms that probably operate in all red supergiants. If Stephenson 2-18 undergoes similar dimming events, we could detect them through photometric monitoring. Long-term light curves would reveal the pattern of mass ejections, helping us estimate the total mass loss rate more accurately. That, in turn, would improve predictions about the star's evolutionary trajectory. The technology exists. What's needed is sustained effort. Monitoring programs that track these stars over years and decades. When something changes, when a star dims or brightens or shows spectral variations, we need rapid follow-up with multiple instruments. Spectroscopy to measure velocities and composition, infrared imaging to map the dust distribution, radio observations to detect masses in the outflowing material. All of this data builds a more complete picture, not just of one star, but of how the largest stars in the universe live and die. Stephenson 2-18 is the current record holder, but records are made to be broken. There might be even larger stars out there, hidden in distant clusters we haven't surveyed yet. Or maybe Stephenson 2-18 really is near the upper limit of what's physically possible. Either way, understanding this star means understanding the extremes of stellar evolution, and it teaches us where the boundaries lie between what's possible and what the laws of physics will never permit. But Stephenson 2-18 doesn't exist in isolation. There's a whole cast of stellar titans competing for the title of largest star, and the rankings shift every time new data arrives. Scutum held the crown for years. Located about 5,900 light-years away in Scutum, the same constellation as Stephenson 2-18, it was measured at over 1,700 solar radii in some studies. That'd make it even larger than Stephenson 2-18. Except those measurements relied on distance estimates that turned out to be wrong. When the Gaia spacecraft measured Scutum's parallax directly, the calculated distance dropped significantly. Closer star, lower luminosity. Lower luminosity means smaller radius to match the observed brightness. The new estimate puts Scutum around 755 solar radii. Still enormous, still one of the largest known stars, but nowhere near the behemoth it was once thought to be. That's the problem with declaring champions in this category. The measurements change, sometimes dramatically. Canis Majoris went through a similar revision. For decades it was considered the largest star known, with estimates reaching 2,000 solar radii or more. Modern analysis puts it closer to 1,420 solar radii. Huge, yes. Record-breaking, not anymore. Then there's WOHG 64, located in the Large Magellanic Cloud. It's one of the few candidates that might actually rival Stephenson 2-18. Estimates place it around 1,540 solar radii, though like all these measurements, there's substantial uncertainty. What makes WOHG 64 particularly interesting is that it's undergoing a dramatic transformation right now. Recent observations suggest it's transitioning from a red supergiant to a yellow hypergiant. That's exceptionally rare. Most stars don't change spectral types on human timescales, but WOHG 64 appears to be doing exactly that, possibly shedding enormous amounts of mass in the process. If that's true, we're watching a star fundamentally alter its structure in real time. Yellow hypergiants occupy a narrow, unstable region of the Hertzsprung-Russell diagram. They're stars in transition, either expanding into red supergiants or contracting back toward hotter temperatures, after a red supergiant phase. The transition period might last only a few thousand years, which means catching a star in this state is like winning the astronomical lottery. And if WOHG 64 is indeed becoming a yellow hypergiant, that tells us something about its future. These transitions often precede supernova explosions. The star might be in its final years, stripping away its outer layers before the core collapse that will end its life, which raises a question. Could Stephenson 2-18 go through a similar transition? Probably not. The evolutionary path depends on initial mass and current mass loss rate. WOHG 64 appears to be losing mass fast enough to expose hotter layers beneath the photosphere. Stephenson 2-18's mass loss rate, while high, might not be extreme enough for that particular path. More likely, it will remain a red supergiant until core collapse. But we can't be certain. That's the recurring theme with these stars. We observe them, we measure them, we build models. But they're so far away, so extreme in their properties, so short-lived on cosmic timescales, that definitive answers remain elusive. The competition for largest star also includes candidates we can barely observe. There are stars in distant clusters we haven't fully surveyed, dense, star-forming regions obscured by dust. Other galaxies where individual stars blend together at our current resolution. Stephenson 2-18 holds the record not because we've checked every star in the universe, but because we've checked the stars we can detect and measure. There might be larger ones out there. We just haven't found them yet. Or maybe we have. Maybe the measurements are wrong in the other direction. Maybe Stephenson 2-18 is actually smaller than we think, and one of the revised estimates for UY Scuti or VY Canis Majoris will turn out to be correct after all. The uncertainty cuts both ways. What we can say with confidence is that red supergiants and hypergiants represent the upper limit of stellar size. No star gets much bigger than this category. The physics won't allow it. Go too large and radiation pressure overwhelms gravity. The star becomes unstable, shedding mass faster than it can maintain its bloated envelope. The Eddington limit defines this boundary. It's the point where outward radiation pressure equals inward gravitational force. For the most massive luminous stars, the actual luminosity approaches the Eddington limit closely. Push beyond it, even temporarily, and the star ejects material in violent outbursts. Luminous blue variables experience this regularly. They're massive stars that undergo episodic eruptions, sometimes brightening by several magnitudes in a matter of weeks. During these outbursts, they exceed their Eddington limit and blow off entire solar masses of material. Eta Carinae famously did this in the 1840s, ejecting more than 10 solar masses in a single event. Red supergiants are more stable than LBVs, but they still hover near their Eddington limits. That's why their mass loss rates are so high. The radiation pressure is almost strong enough to levitate the photosphere. Material in the outer layers feels an outward force nearly equal to the inward pull of gravity. It doesn't take much to tip the balance and drive mass loss. For Stephenson 2-18, with its luminosity of 440,000 suns, the radiation pressure is immense. The star is constantly fighting against its own light. Every photon generated in the core eventually makes its way to the surface, and each one carries momentum. Billions upon billions of photons per second, all pushing outward. At the photosphere, where the star becomes transparent and light escapes freely, that outward push is at its maximum. atoms and molecules in the outermost layers feel the full force of the radiation field. For heavy elements, especially metals like iron, the cross-section for absorbing photons is large. Those atoms get pushed more than lighter elements like hydrogen and helium. This selective pressure creates a wind. Material streams away from the star, accelerating as it moves outward. Near the photosphere, the wind might be moving at a few kilometers per second. Farther out, it reaches tens of kilometers per second. The material carries away mass, angular momentum, and energy. Over time, this wind reshapes the star. The envelope slowly shrinks. The radius decreases. The surface temperature might rise slightly as deeper, hotter layers become exposed. The star evolves, driven as much by mass loss as by nuclear burning in the core. How long can this continue? For red supergiants in general, the mass loss phase might last a few 100,000 years. For a star as large and luminous as Stephenson 2-18, it could be shorter, maybe only tens of thousands of years before the envelope is depleted or the core reaches a critical state. And then what? Most likely, core collapse. The iron core grows until it exceeds the Chandrasekhar limit, roughly 1.4 solar masses. At that point, electron degeneracy pressure can no longer support it. The core implodes in less than a second, reaching nuclear densities. Protons and electrons merge into neutrons. The collapse halts abruptly when the core becomes a solid ball of neutrons, incompressible at those densities. The rebound launches a shockwave outward through the star. That shockwave doesn't carry enough energy by itself to blow apart the envelope. It stalls a few hundred kilometers from the core. But neutrinos, streaming outward by the trillions, deposit a fraction of their energy into the stalled shock. That's enough to revive it. The shock accelerates outward, tearing through the star's outer layers in a matter of hours. The supernova becomes visible when the shock reaches the photosphere. For Stephenson 2-18, with its enormous radius that could take weeks or even months, light from the explosion would take that long just to cross the star's diameter. Once the shock breaks through, the star brightens dramatically. At peak, a supernova can outshine an entire galaxy. For a few weeks, it's the most luminous object in its cosmic neighborhood, radiating energy at a prodigious rate. Then it fades. The expanding debris cools. Heavy elements synthesized in the explosion or in the final moments of core collapse spread into space. That material will eventually become part of new stars, new planets, maybe even new life. But there's another possibility. Maybe Stephenson 2-18 won't explode as a supernova. The red supergiant problem suggests that the most massive red supergiants might not produce visible explosions. Observations show that stars above a certain mass and luminosity threshold simply disappear. They're there 1 year, gone the next, with no supernova detected in between. One explanation is that these stars undergo direct core collapse to a black hole. The shock wave stalls and never revives. The entire star, envelope and all, falls into the newly formed black hole. No explosion, no ejected material, just a black hole where a star used to be. Another explanation involves thick dust shells. If the star is surrounded by enough dust, the supernova light might be absorbed before it can escape. The explosion happens, but we don't see it. Infrared observations could detect the dust heating up, but in optical wavelengths, the event would be invisible. Recent discoveries support this second scenario. A few supernovae have been found where the progenitor star was hidden by dust. The explosion itself was detected, but only because instruments sensitive to infrared or radio wavelengths were observing at the right time. If Stephenson 2-18 is surrounded by a dense dust shell, and if it explodes, we might miss the event entirely. Or we might see a faint, reddened outburst that doesn't look like a typical supernova. The dust would absorb the optical light, re-radiate it in the infrared, and create a confusing signal that could be misinterpreted. This matters for understanding stellar evolution and for predicting what we should see when these giants die. If we're missing supernovae because dust hides them, our models need to account for that. If stars collapse directly to black holes, that has implications for black hole formation rates and the distribution of black hole masses. Stephenson 2-18 might provide answers, or it might deepen the mystery. When it dies, if we're lucky enough to observe the event, we'll learn something fundamental. If it disappears quietly, that's also information. Absence of evidence becomes evidence of absence, or at least evidence of thick dust. For now, it sits in Stephenson 2, blowing off mass, pulsating gently, radiating energy into space. How much longer it will continue is unknown. Could be tomorrow. Could be 100,000 years from now. The uncertainty is frustrating, but also oddly fitting. These stars exist at the edge of what's possible. Their extreme properties push our models to the breaking point. They're rare enough that we have limited data, far enough away that measurements are difficult, variable enough that nothing stays constant for long. In a sense, the fact that we can study them at all is remarkable. We're talking about objects 18,900 light-years away, glowing so brightly they're visible across that distance, large enough that their properties fundamentally challenge our understanding of stellar physics. Every observation adds a piece to the puzzle. Every revision to the measurements refines our picture. Every new discovery of a similar star gives us more data points to constrain the models. Stephenson 2-18 is the current record holder, the largest star we know of, the benchmark against which all other giants are measured. Whether it remains the champion or gets dethroned by future discoveries almost doesn't matter. What matters is what it represents. The absolute limit of stellar size. The endpoint of massive star evolution. A cosmic laboratory where gravity, radiation, and nuclear fusion battle for supremacy, and we get to watch from a safe distance, learning as we go. Beyond Stephenson 2-18, there's a wider question. What determines the absolute upper limit for stellar size? Physics doesn't care about titles or rankings. There's some maximum radius a star can achieve before something breaks, before gravity wins, or radiation pressure tears it apart, or mass loss strips away the outer layers faster than fusion can sustain them. The Eddington limit defines one boundary. When radiation pressure pushing outward equals gravitational force pulling inward, you've hit equilibrium. Push past that, and the star starts ejecting its own photosphere. Light becomes powerful enough to lift material off the surface and blow it into space. For hypergiants operating near this threshold, stability is fragile. Small fluctuations in luminosity can trigger mass ejection events. The star literally sheds pieces of itself to avoid crossing the line. But there's another constraint. Convection. Red supergiants have massive convective envelopes. Hot plasma rises from deep inside, cools at the surface, then sinks back down. This cycle transports energy and prevents the core from overheating. As the star expands, these convective cells grow enormous, hundreds of solar radii across. The timescale for material to complete one cycle stretches to years or decades. At some point, convection becomes inefficient. Energy transport slows. The core heats up. Instabilities develop. Models suggest there's a maximum effective radius around 2000 to 2500 solar radii, where convection starts failing. Beyond that, the star can't maintain equilibrium. It either contracts, ejects mass, or undergoes some catastrophic restructuring. Stephenson 218 sits right at this edge. If the 2150 radius estimate is accurate, it's operating at the theoretical limit of what a red supergiant can sustain. This implies something provocative. We might have already found the largest possible star. Not just the largest currently known, but the largest that can physically exist given the laws of stellar physics. Future discoveries might refine measurements, might find competitors with similar sizes, but they probably won't find anything dramatically larger. Not unless our models are fundamentally wrong. Of course, there's always the possibility of outliers. Extreme mass, unusual composition, temporary states during rapid evolution. VY Canis Majoris demonstrated how complex these objects can be. Its surrounding nebula contains knots and arcs of ejected material, some moving at different velocities, suggesting multiple ejection events over time. The structure isn't symmetric. Different regions show different compositions. Some areas are oxygen-rich, others carbon-rich, which shouldn't happen in a single star unless it's undergone significant internal mixing or captured material from a companion. That raises another wrinkle. Binary evolution. Many massive stars exist in binary systems. Two stars orbiting each other, close enough that they can exchange mass. One star evolves faster, swells into a giant, and starts dumping material onto its companion. The companion gains mass, the giant loses it, and both stars end up in configurations they wouldn't achieve alone. Could Stephenson 2-18 have a hidden companion? Could mass transfer explain some of its properties? There's no evidence for it, no orbital motion detected, no signs of a second star. But at 18,900 light-years, resolving a companion would be nearly impossible unless it's also extremely luminous. A neutron star or black hole companion would be invisible. A main sequence star would be drowned out by Stephenson 2-18's glare, so we can't rule it out. If a companion exists, it might affect the ultimate fate. Binary systems produce different supernova outcomes than single stars. The companion can strip away the hydrogen envelope before the primary explodes, creating a Type 1b or 1c supernova instead of a Type 2. Or the companion could accrete enough mass to eventually explode itself. Or, in rare cases, the two stars could merge, creating something even more extreme. Merger scenarios are speculative, but worth considering. If two massive stars collide and coalesce during their red supergiant phase, the result would be a single object with combined mass and angular momentum. Depending on how the merger proceeds, you might get a temporarily inflated envelope, higher luminosity, and unusual surface composition. The merged star wouldn't be stable long-term. It would readjust over thousands of years, possibly ejecting mass, possibly collapsing inward. But during the transient phase, it could appear extraordinarily large. No evidence suggests Stephenson 2-18 is a merger product. It's just one possibility among many. The point is that stellar evolution at these extremes involves mechanisms we're still working to understand. Every assumption carries uncertainty. Every model has limitations. Distance remains the most fundamental problem. Stephenson 218's size estimate depends critically on its assumed distance of 5.8 kiloparsecs. That number comes from cluster membership. Stephenson 2 is a young, massive cluster, and kinematic studies suggest it's about 18,900 light-years away. But what if Stephenson 218 isn't actually in the cluster? What if it's a foreground or background object that just happens to appear in the same region of sky? Unlikely, but not impossible. The star's radial velocity matches the cluster. Its reddening matches. Its age seems consistent with other cluster members. Everything points toward physical association. But until we get a direct parallax measurement, there's always residual doubt. Gaia, the European Space Agency's astrometry mission, has been measuring parallaxes for billions of stars. But Stephenson 2-18 is faint, distant, and embedded in a crowded field. Early Gaia data releases didn't include it. Future releases might. If they do, we'll have a direct distance measurement independent of cluster assumptions. That could revise the size estimate up or down by significant margins. Scutum went through exactly this process. For years, it was cited as the largest known star with a radius around 1,700 solar radii. Then Gaia measured its parallax. The star turned out to be closer than assumed. Closer distance means lower luminosity. Lower luminosity means smaller radius. The updated estimate dropped to around 755 solar radii. Still huge, but less than half the previous value. The largest star became just another large star. Could the same happen to Stephenson 2-18? Absolutely. If Gaia reveals it's closer than we think, the radius shrinks proportionally. If it's farther, the radius grows. The uncertainty cuts both ways. We won't know until the data arrives. WOHG 64 offers an interesting counterpoint. It resides in the Large Magellanic Cloud, a satellite galaxy orbiting the Milky Way. Distance to the LMC is well established at about 160,000 light-years. No ambiguity there. WOHG 64's properties are therefore better constrained than galactic stars at comparable distances. Its radius is estimated at 1,540 solar radii with relatively tight error bars. Recent observations detected dramatic changes. The star dimmed significantly between 2014 and later observations. Spectral analysis suggests it transitioned from a red supergiant to a yellow hypergiant. If confirmed, that's extraordinary. Stars don't usually change spectral types on human timescales. The transformation might signal an impending supernova. Yellow hypergiants represent a brief transitional phase between red supergiants and final collapse. The star is contracting, heating up, shedding mass violently. This phase lasts perhaps a few thousand years, a blink in cosmic terms. Catching a star mid-transition is rare. If WOHG 64 explodes soon, we'll witness a supernova in a neighboring galaxy with a well-documented progenitor. That would be invaluable data. But soon, in astronomy, means something different than in everyday life. Soon could be next year, could be 1,000 years. We don't know. The star could stabilize, expand back into a red supergiant, and continue for another 100,000 years. Or it could explode tomorrow. The uncertainty is maddening, but unavoidable. All these stars, Stephenson 2-18, VY Canis Majoris, WOHG 64, UY Scuti, exist in the same evolutionary neighborhood: massive, evolved, unstable. They're all approaching the end. They're all grappling with the same physics: radiation pressure, mass loss, convection, nuclear fusion. The same fundamental forces govern them all, yet each behaves slightly differently. Each has unique quirks, unusual properties, individual histories. That diversity matters. It tells us stellar evolution isn't a simple linear process. There's no single path from main sequence to supernova. Stars of similar mass can evolve differently depending on rotation, composition, mass loss history, magnetic fields, binary interactions. The final state depends on the journey. Stephenson 218's extreme size might be temporary, a phase it's passing through before contracting or exploding. Or it might represent the star's equilibrium state for this stage of evolution, maintained for tens of thousands of years. We can't tell from a single snapshot. We need long-term monitoring, observations spanning decades or centuries to track changes in luminosity, radius, mass loss rate, surface composition. Only then can we reconstruct the full story. Some of this monitoring is already happening. Amateur astronomers track red supergiants photometrically, recording brightness variations over years. Professional surveys revisit these objects periodically, checking for changes. Space telescopes image them in infrared, penetrating the dust to see the central star. Radio observations detect mass emission from surrounding gas, tracing outflows and magnetic fields. Each technique adds another piece of information. Eventually, the accumulated data will paint a clearer picture. We'll understand how these stars evolve, what triggers their instabilities, how they lose mass, when they explode. We'll refine the theoretical models until they match observations. We'll push the boundaries of measurement until uncertainties shrink to acceptable levels. But that takes time. Decades, probably, maybe longer. For now, Stephenson 218 holds the title. Largest known star, a behemoth at the edge of possibility, defying theoretical predictions, challenging our understanding, and reminding us how much we still don't know. It's a placeholder in some sense, a temporary answer to a question that will keep evolving as technology improves and data accumulates. But it's also a real object, a physical star shining in the night sky, visible if you know where to look and have the right equipment. Its photons travel 18,900 years to reach Earth, carrying information encoded in wavelengths of light. That information tells a story about stellar physics, about nuclear fusion, about the life cycle of matter in the universe. The story is incomplete, full of gaps and uncertainties, but it's being written, one observation at a time. And every observation refines our understanding of how these monsters behave. What makes them expand? What drives their mass loss? What determines their final fate? Think about the sheer scale of uncertainty involved. Stephenson 218's radius could be off by hundreds of solar radii. Maybe it's 2,000, maybe 2,300. The measurement techniques have margins wide enough to swallow multiple solar systems. That's not a criticism, it's just reality. These stars are incredibly distant. Their atmospheres are fuzzy, irregular, pulsating. They're surrounded by thick shells of ejected material. Getting precise measurements is genuinely difficult. Distance errors compound everything. If Stephenson 2-18 is actually closer or farther than 18,900 light-years, all the derived properties change. Luminosity scales with distance squared. Get the distance wrong by 10%, and luminosity shifts by 21%. That changes the inferred radius, changes the evolutionary interpretation, changes everything. Parallax measurements help. Gaia revolutionized distance estimates for many stars, but Stephenson 2-18 is too distant for reliable parallax. We're stuck using cluster membership, spectroscopic distances, other indirect methods. Each has assumptions, each introduces uncertainty. Future missions might improve this: better infrared telescopes, interferometry with longer baselines, direct imaging of stellar surfaces. Technology advances, measurements improve. What seems impossible today becomes routine tomorrow. But some limitations are fundamental. Light takes time to travel. We're always seeing these stars as they were thousands of years ago. By the time we observe them, they've already moved on, changed, evolved into something different. We're studying history, not the present. That temporal disconnect matters. If Stephenson 2-18 exploded today, we wouldn't know for 18,900 years. The star could be gone, dispersed into a nebula, and we'd still be analyzing it as if it existed, cataloguing its properties, calling it the largest star. Meanwhile, reality has already moved forward. This happens constantly in astronomy. Every observation is archaeology. Every measurement is a fossil record. We piece together the past and extrapolate into the future. But the present remains forever out of reach. The philosophical implications are strange. When we ask, what is the largest star? We're really asking, what was the largest star thousands of years ago? The current title holder might not exist anymore, might have already detonated, might have contracted back down. We'll never know until the light reaches us. That's frustrating, but unavoidable. The speed of light is finite. Distances are vast. Information propagates slowly. We work with what we have. And what we have is remarkable. Despite all the uncertainties, despite all the limitations, we've identified dozens of stellar behemoths. We've measured their properties within reasonable margins. We've constructed theories that explain their existence. We've predicted their futures. Stephenson 2-18 will likely explode. The physics demands it. Stars this massive don't fade quietly. They don't shrink into white dwarfs. They reach a critical point where the core collapses, rebounds, and blows the entire star apart. Supernova. When? That's the impossible question. Could be tomorrow. Could be 1,000,000 years. The timescales involved are so short compared to most stellar evolution that predicting the exact moment is hopeless. We can say soon on cosmic timescales, but that's not particularly useful. What we can say is this: when it happens, it'll be spectacular. A supernova this distant won't be visible to the naked eye, but telescopes will catch it. The light curve will tell us about the explosion mechanism. The spectrum will reveal what elements were created in the blast. The remnant will show us what's left behind. That data will be invaluable. Every supernova observation refines our models, tells us more about nuclear physics, shock waves, neutrino emission, gravitational collapse. These events are laboratories for extreme physics, conditions we can't replicate on Earth, pressures, temperatures, densities that exist nowhere else. Red supergiants produce Type 2P supernovae. The P stands for plateau. After the initial brightening, the light curve flattens for weeks or months before declining. This happens because the star's extended hydrogen envelope takes time to recombine and cool. The plateau phase is diagnostic, tells us about the progenitor's structure. Stephenson 218's supernova will likely fit this pattern. Massive hydrogen envelope, gradual decline, long plateau. But there could be surprises. Unusual mass loss history might create unexpected features. Circumstellar interaction could brighten the explosion. Binary effects might complicate things. We won't know until it happens. And when it does, astronomers worldwide will mobilize. Telescopes will swing toward it. Spectroscopy will begin immediately. Monitoring will continue for years. Every photon will be analyzed. The remnant will persist for millennia. An expanding shell of gas enriched with heavy elements. Oxygen, silicon, iron, all the products of nuclear synthesis scattered into space. That material will eventually form new stars, new planets, new possibilities. This is how the universe recycles itself. Massive stars forge heavy elements. Supernovae distribute them. New generations of stars incorporate that enriched material. The process continues, generation after generation, increasing the metallicity of the galaxy. Our solar system contains elements from supernovae. The iron in your blood was created in a stellar core and expelled in an explosion billions of years ago. You're made of star stuff, literally. The atoms in your body were forged in nuclear furnaces and scattered across space. Stephenson 218 will contribute to that cycle. When it explodes, its enriched material will spread outward at thousands of kilometers per second. Some of it will encounter dense molecular clouds. Compression from the shockwave might trigger new star formation, and those new stars will contain atoms from Stephenson 218's interior. In a sense, the star will live on, not as a coherent object, but as dispersed material incorporated into countless other systems. A legacy written in atomic nuclei across the galaxy. That's the ultimate fate of all massive stars. They don't persist. They transform. They become something else. Nebulae, neutron stars, black holes, but also future generations of stars and planets. The cycle is continuous. Stephenson 2-18 is just one participant in this grand process. Temporary, transient, doomed, but significant nonetheless. It represents an extreme case, a boundary condition, a test of theoretical limits. Its existence proves that stars can reach these sizes under the right conditions. That stellar evolution allows for such extremes. That the Eddington limit can be approached but not exceeded for extended periods. It also raises questions. Why aren't there even larger stars? What prevents them from growing indefinitely? The answer involves radiation pressure, mass loss, and instability. Beyond a certain point, the star can't hold itself together. Radiation blows off the outer layers faster than they can accumulate. The star reaches equilibrium or exceeds it and self-destructs. Stephenson 2-18 might be near that limit. Its extreme mass loss suggests it's struggling to maintain stability. The radiation pressure is enormous. The gravity barely contains it. One wrong move, one internal fluctuation, and the balance could tip. If it tips toward instability, mass loss accelerates. The star sheds its envelope rapidly. What remains might contract, heat up, evolve into a different type. Yellow hypergiant, luminous blue variable, Wolf-Rayet star. Each stage has different characteristics, different appearances, different fates. Or it might tip toward collapse. The core reaches critical density. Fusion stops. Gravity wins. Collapse begins. In seconds, the core compresses into a neutron star or black hole. The outer layers fall inward, hit the rebounding core, and explode outward. Supernova. Both paths are possible. Both have precedent. WOHG 64's recent transformation toward yellow hypergiant status suggests the first path can happen, but most red supergiants probably follow the second. Explode rather than evolve. Statistical studies help. By observing many red supergiants, astronomers can determine which outcomes are more common. What percentage explode directly? What percentage evolve into other types first? The data is still incomplete, but patterns are emerging. Most red supergiants below a certain mass explode. Above that mass, evolution might intervene. The star might shed enough mass to avoid immediate collapse, might transform into something else, might delay the inevitable for thousands of years. Stephenson 218's fate depends on its current mass. If it's retained most of its original mass, it'll likely explode soon. If extreme mass loss has reduced it significantly, it might evolve instead. We don't know which scenario applies. Estimating current mass is difficult. Initial mass can be inferred from evolutionary models. But how much has been lost? The mass loss rate gives a clue. Multiply by the time spent in this phase. But we don't know that time precisely. Could be 10,000 years. Could be 100,000. This uncertainty pervades everything. Every question about Stephenson 2-18 leads to more questions. Every answer comes with caveats. The star exists in a fog of unknowns. Yet that's what makes it interesting. If everything were certain, there'd be no mystery, no reason to keep observing, no discoveries waiting. The uncertainties are what drive research forward. Astronomers will keep watching Stephenson 2-18, monitoring its brightness, checking for changes, comparing it to models. Slowly, data will accumulate, understanding will deepen, and eventually, maybe decades from now, we'll have a clearer picture. Or it'll explode first, and then we'll learn everything in one dramatic event. Either way, the story continues. For now, it remains the largest known star, a record holder with an asterisk, a provisional answer to a question that might not have a permanent answer. Because the universe doesn't care about our categories, doesn't care about records or rankings. It just is. Stars form, evolve, die. Some get big, some get enormous. A few push the absolute limits. Stephenson 218 is one of those few, a giant among giants, a behemoth at the edge of what's physically possible. And somewhere out there, beyond our current observational reach, there might be something even larger. A star we haven't discovered yet. One that dwarfs even Stephenson 218. It's possible. The universe is vast. Our surveys are incomplete. Future telescopes will find it if it exists. The James Webb Space Telescope is already revealing previously hidden objects. Next-generation ground-based telescopes will push further. Space-based infrared observatories will penetrate deeper into dust-shrouded regions. Each new capability brings new discoveries. The title of largest star might change hands multiple times in coming decades. New measurements will revise old estimates. New discoveries will challenge current records. That's how science works. Provisional answers replaced by better ones. But the fundamental question remains compelling. How large can a star actually get? What's the theoretical maximum? Where does physics draw the line? Models suggest an upper limit somewhere around 2,500 to 3,000 solar radii. Beyond that, instabilities dominate. Radiation pressure tears the star apart. Mass loss becomes catastrophic. The object can't maintain coherence. Stephenson 2-18 approaches that limit. It's in the neighborhood of maximum possible size. Whether it represents the true maximum or just our current observational limit remains to be seen. Either way, it's a spectacular object, a testament to the universe's ability to create extremes, a reminder that nature operates on scales that dwarf human comprehension. When you look up at the night sky, remember that up there, invisible to your eyes, are stars thousands of times larger than the sun, giants beyond imagining. Objects so vast they redefine what large means. Stephenson 218 is one of them, and it's still out there, shining, evolving, approaching its inevitable end. So where does this leave us? Stephenson 218 sits nearly 19,000 light-years away, radiating with the fury of 440,000 suns, stretching to a radius that would swallow Jupiter if it replaced our star. By current measurements, it's the largest known star in the universe. But that title comes with conditions: distance uncertainties, measurement limitations, pulsation cycles, dust obscuration. Any of these could shift the numbers tomorrow. Scutum held the crown until better data cut it down to size. Canis Majoris dominated for decades before revisions knocked it from the throne. WOHG 64 might be larger if its recent transformation hasn't altered its structure too dramatically. The rankings shift with every new observation, every refined measurement, every satellite that improves our view of the cosmos. The real answer isn't a single star, it's a category. Red supergiants and hypergiants represent the absolute upper limit of stellar size. Physics won't allow much larger. The Eddington limit defines one boundary. Radiation pressure equals gravitational force. Cross that line and the star tears itself apart. Convection provides another constraint. Expand too far and energy transport breaks down. The envelope becomes unstable. Something has to give. Stephenson 2-18 exists right at these limits. It's operating in a regime where small changes trigger dramatic effects. Mass loss accelerates. Pulsations intensify. The star dances on the edge of catastrophe, held together by forces that barely balance. How long it maintains this precarious state is unknowable. Could be millennia, could be tomorrow. When it ends, we'll learn something fundamental. If it explodes as a supernova, we'll measure the properties of one of the most massive stellar detonations in galactic history. If it collapses directly to a black hole, that tells us about the upper limits of supernova physics. If dust hides the event, we'll understand why so many massive stars seem to disappear without visible explosions. Each outcome provides data. Each observation refines models. The accumulated evidence from Stephenson 2-18, Canis Majoris, Betelgeuse WOHG 64, and dozens of others gradually paints a clearer picture of how the largest stars live and die. But here's what matters most. These aren't just astronomical curiosities. They're cosmic engines. They forge heavy elements in their cores. They scatter those elements across space when they explode. They trigger new generations of star formation. They shape the chemical evolution of galaxies. The iron in your blood came from a supernova. The oxygen you breathe was created in a massive star's core. The calcium in your bones, the carbon in your cells, all of it originated in stellar furnaces like Stephenson 218. When it explodes, it'll contribute to that cycle. Material from its interior will spread across light years, eventually incorporating into new stars, new planets, maybe even new life. You're made of star stuff. That's not poetic metaphor, it's literal fact. The atoms comprising your body were forged billions of years ago in stars that no longer exist. They were scattered by supernovae. They drifted through space. They accumulated in a molecular cloud that collapsed to form our solar system. And now they're temporarily arranged into the pattern you call yourself. Stephenson 2:18 will follow the same path. Its atoms will disperse. They'll become part of future systems. The star itself will vanish, but its material persists, recycled endlessly through cosmic generations. The question of whether it's truly the largest star becomes almost irrelevant in that context. What matters is what it teaches us about stellar physics, about the limits of size and luminosity, about how matter behaves under extreme conditions. What matters is the role it plays in the grand cycle of cosmic evolution. Future discoveries will probably find larger candidates. Better measurements will revise current estimates. The title will change hands again. That's expected. That's how science works. But the fundamental understanding we've gained from studying these objects endures. We know stars can reach truly staggering sizes under the right conditions. We know they can't grow indefinitely. We know they're unstable, short-lived, and violent. We know they're crucial for galactic chemical evolution. We know they represent the endpoints of massive stellar evolution. Stephenson 2:18 embodies all of this. It's a laboratory for extreme physics, a natural experiment running at scales we can't replicate, a window into processes that shaped the universe and made life possible. So yes, it's probably the largest star we currently know about. But more importantly, it's a reminder that the universe operates on scales that dwarf human comprehension. That nature creates extremes we're only beginning to understand. That every answer leads to new questions. Somewhere out there, beyond our current observational limits, there might be something even larger. A star so massive it makes Stephenson 2:18 look modest. We haven't found it yet. Maybe we never will. But the search continues, because that's what drives astronomy forward. Not the answers, but the questions. Not the certainty, but the mystery. Not knowing exactly where the boundaries lie, but pushing against them anyway, seeing how far we can go. Stephenson 2:18 represents one boundary, the edge of stellar size, the limit of what current physics predicts. Whether it's the true maximum or just our current understanding remains to be seen. Either way, it's out there right now, shining across 18,900 light-years of space, shedding mass into the void, approaching its inevitable end, and we're fortunate enough to witness it, to measure it, to marvel at what the universe is capable of creating. The largest known star, a behemoth at the limits of possibility, a temporary answer to an eternal question, and a reminder that no matter how much we learn, there's always more to discover.